duck? You know, gray duck or mountain desert? No. What do you do?
Make sure you guys have a calculator again today. We're gonna need it. Alright, so before we continue with these parametrics from yesterday, Eric asked a question yesterday that was pertaining, I think, to, oh wait, you can't see it. On the first page, when we were kind of graphing these on our calculator, we saw that this set of parametric functions gave a very similar shape graph to the first set. And Eric asked, well, I refer to it as the same equation, and Eric asked, how could that be? Or do you just mean the same shape? Do you remember that question?
Yeah, 'cause you said well, it looks like the same graph, and I said it looks like the same graph, it's different points, and then there was so much shape.
Say it again. You said they were different points.
Yeah, they had different points, but you said they were the same graph, so I was confused.
Okay. They actually are the same graph. So I had to go back and think about it.
We were like whispering to each other, we were like,
No, because I graphed it both
Yeah?
and looked at the tables for them, and like
Okay, well
X and Y tables were different.
the X and Y tables are different because you're looking at different points in time. So for this set of parametric equations, at time -2, you would get a particular ordered pair.
I looked at the same time things.
You did too? Okay,
I
so
went from -2 or -3 to 3 for each of them, and the tables were
they were different?
different.
Okay, well maybe we'll investigate that today because I want to show you how they actually are the same graph exactly. Because when we eliminated this parameter of t, we got this rectangular equation with x's and y's. If you do the same thing with these, you're actually going to get the same rectangular equation, which means it should be the same graph. So if you take y and plug it in there, x equals 4, y squared minus 4, you can add 4, divide 4, and then square root both sides. Notice how it's the same exact equation. So these are the same exact graph, which means they should have the same exact points, but the points on this graph might correspond to different points on this one because of their time values. So I'm curious as to how you typed it in on here to get your tables. Do you remember how you did it, or if it's still in there by chance?
It is not still in there.
Okay, so we're,
I think I just typed in the x graph, which was the -4 squared minus 4, and then the y graph, which was t.
yep,
Then I went over to the table set.
yep. Did you change your Tmin and Tmax on your window?
I kept the on the window.
Mm-hmm.
No, I think I put it to -3, 3.
-3 for both. Okay,
So that way I could compare it to the one above.
sure.
Then the t step was 1, like the one above, and then table set I had it started -3,
Okay,
and then had it go by 1s,
ones. Okay.
and then we did
Do you have it set to auto or ask?
uh,
Do you want the calculator to
I had
generate
it
the
first
values?
ask and then dependent is auto. Yeah.
Gotcha. Okay, so then,
So it gives us that, which is not the same table we had above when we wrote out the table.
okay, so what that's telling you is that the -2 time for this graph and the -2 time, I know it's not in this window, but you made it -3 to +3. The -2 time for this parametric set and the -2 time for this parametric set do not correspond to the same point.
Correct.
But they do have the same point in common. It just means you're at, so I think the graph yesterday kind of looked like that.
Yeah.
For this graph, I think -2 time corresponded there. That was our beginning spot. But this point might have a different time value to be at that location. For instance,
Okay.
I don't know, it would be -1. Yeah, see how you still have the same ordered pair, it's just that for this parametric set, it's time -1, whereas for this parametric set, it was time -2. So at a different point in time, you're at the same location, depending on which set you have. Okay, so to kind of correct myself from yesterday, yes, they are the same shape, but they actually are the same graph. Okay? Does that kind of make sense to the...
Yeah.
Okay. Good. Okay, so let's go ahead and we're going to dive into the calculus today with these parametric equations. We were getting used to kind of what they are, how we can use our calculator to graph them. But parametric sets always have an x equation and a y equation with some type of parameter in there. Normally it's t, sometimes it could be theta, okay, a different variable, but we have some other variable or parameter to consider. So what's nice about these parametric equations is that derivatives kind of work the same way they normally do for rectangular ones. What can get a little tricky though is the second derivative of these parametric equations. So we'll spend a bit of time just going over this. I don't expect you to remember kind of this process, but we are going to talk about what the ending result is. So second derivatives for parametrics don't quite work the same way as second derivatives for rectangulars. So normally when you're given an x equation and a y equation, specifically with a variable t, we'll say, if you were to take the derivative of the y equation with respect to t, that would look like dy over dt. And if you were to take the derivative of the x equation with respect to t, that would be dx over dt. Now we're used to seeing a derivative notation represented by dy over dx, because when we're using a regular rectangular equation, we have x's and y's. But now we have this other parameter of t. So I'm hoping, if it makes sense, what if we were to take the y derivative equation and divide it by the x derivative equation as such? Okay? If you were dividing a fraction, what's the same or what's a similar operation? Instead of dividing by dx over dt, what else could you do? Multiply by the reciprocal, which would be dt over dx, right? And notice how the dt's would cancel, and you're left with dy over dx. So the way you find a derivative for these parametric equations is you simply take the y derivative divided by the x derivative. And hopefully that might be a little obvious just with the way that dy over dx is written. You can take the y derivative divided by the x derivative. Okay? Does that kind of click? Do we see that? All right. What's a little more tricky is figuring out a second derivative. Very rare that we'll come across these, but we will practice them nonetheless. And it might be a little difficult for us to start with the second derivative notation and work to the right. So instead, we're going to start on the right-hand side and kind of work our way backwards to show you how it represents the second derivative. So this numerator up here is telling us to take the derivative with respect to time of the first derivative that we can find this way that we just said. And then we'll divide it by dx over dt. What does that represent? Dx over dt? That's the derivative of the x equation. Okay, so very similar, instead of dividing by a fraction, you can multiply by its reciprocal. Do you see how I brought that up and multiplied by dt over dx? Okay, notice how the dt's will cancel, right? So we're left with d dy over dx dx, And if you were to essentially imagine multiplying across, d times dy would be d squared y, and dx times dx is dx squared. Okay? So in a nutshell, we need to figure out the derivative of the first derivative and then divide that by the x derivative equation. A little tricky for these parametrics because we're dealing with two functions now instead of one. So to figure out the second derivative for parametrics, we need to take the derivative of the first derivative divided by x equation derivative. Okay, so in a nutshell, doing that process eventually leads us to d squared y over dx squared, which is the notation for a second derivative for rectangular functions. So we're going to try to practice this today without a calculator for this one. So they want us to find the first derivative and the second derivative and then evaluate both of those at 1. Okay, let's go ahead and first maybe figure out the derivatives of the individual equations. So let's check out the derivative of the x equation with respect to time. Can we take the derivative of 2 square root of t? Maybe you want to write it as 2t to the 1/2 to help you out. What would that look like? T to the negative 1/2 power. And then maybe you want to rearrange it so that it's no longer a negative power. That would be 1 over the square root of t. All right, let's go ahead and find the derivative of the y equation with respect to time. That one's a little bit easier. We'd have 6t minus 2. All right, so now that we have the individual derivatives, how can we use those to figure out the kind of overall first derivative of the parametric set, dy over dx? What can we do with these individual derivatives? Divide them. Which one goes up top?
6t
Yeah.
minus 2.
All right, so we need the derivative of the y equation, 6t minus 2, divided by the derivative of the x equation, which would be 1 over the square root of t. Now maybe we can clean it up. Instead of dividing by 1 over the square root of t, you can multiply by the reciprocal, which would just be the square root of t. And if you wanted to keep going, we could distribute in the square root of t. So that would be 6 times t to the 3/2 power. Okay, you'd have to add your exponents. Minus 2 square root of t. All right, so there's the overall first derivative. And they want us to evaluate that at 1. So if we were to plug in 1 for both of those t's, what do we get? We get 4. Yeah? Okay. Let's go ahead and check out the second derivative. So this one is a little bit more involved. So the second derivative, we said, was the derivative of the first derivative divided by the x derivative equation. So if we were to take the derivative of the derivative we just found, using our little shortcuts, we'd have 9t to the 1/2 minus t to the negative 1/2. Okay, taking the derivative of the first derivative. And then we would divide that by the x derivative equation, which we said was 1 over the square root of t. Again, maybe we can clean that up a little bit. Instead of dividing by a fraction, you can multiply by the reciprocal. And maybe we want to distribute in the square root of t. So a square root of t times another square root of t, okay, t to the 1/2 power, would just be t, because the square roots would go away. And then what about the square root of t times t to the negative 1/2? What's going to happen there? Maybe you want to change, instead of square root of t, you want to change it to t to the 1/2 power to help you out. When you multiply the same base, what do you do with the powers? You add them, right? So that would be t to the 0, but what's that? 1. Good. Okay, so there's our overall second derivative. And they want us to plug in 1, so looks like we get 8. All right, so moral of the story. For parametric functions, the first derivative is just as simple as taking the y derivative over the x, but the second derivative for parametric is a little bit more involved. You have to take the derivative of the first derivative you found, but then divide it by the x derivative. Okay? We're going to try another one. Let's see. All right, without a calculator, given that parametric set, write the equation of a tangent line to the curve at that time. What information do we need to know to write the equation of a tangent line? Point and slope. Okay, I lovingly beat it into you guys last year. Okay, point and slope. So the point, we need an x-coordinate and a y-coordinate. But we have an x equation and a y equation because a parametric set has 2 pairs. So we're going to have to plug in 3 pi over 4 into the x equation to get the x coordinate, and 3 pi over 4 into the y equation to get the y coordinate. So you kind of have one more step here, because whenever you're dealing with a parametric, or not parametric, a rectangular set, you only have to plug it into the original function to get the point. But now that we have 2 functions, we'll have to check both. So since this is without a calculator, we got to think about our unit circle. Cosine and sine of 3 pi over 4. So that would be right there on the unit circle, right in the middle. Can you think about what the cosine and sine values are at that point? Do you know what the coordinate looks like in the middle of a quadrant? For both of them. Yeah. Yep, they're both the same. All right, now since we're in the second quadrant, cosine would be negative. because it's like an x value, and then sine would be positive because it's like a y value. So for the x coordinate, if we did 4 times that square root of 2 over negative square root of 2 over 2 value, we would get negative 2 square roots of 2, because the 4 and the 2 in the denominator could simplify. But it doesn't look like anything will simplify for the y coordinate. So we'll have 3 square root of 2 over 2. Alright, so there's our point. Next, we got to figure out the slope. So derivative, we have dy over dx. We need the derivative of the y equation divided by the derivative of the x equation. So derivative of 3 sine would be
Just
3 cosine, yep. And the derivative of 4 cosine, negative 4 sine, good. All right. If we were to plug in that time of 3 pi over 4, okay, we're still using that same coordinate from the unit circle. So we'd have 3 times negative square root of 2 over 2, and then in the bottom, negative 4 times square root of 2 over 2. Let's simplify it. Since this is a fraction, we have a square root of 2 up top and another square root of 2 over 2 on the bottom. So those would cancel. And we're essentially left with a negative 3 over negative 4, which would just be 3/4. So we know the point, the x and y coordinate, and the slope. Let's go ahead and write our equation. Y minus 3 square root of 2 over 2 equals 3/4 times x plus 2 square roots of 2. You doing okay so far? Let's check out the next one. Without a calculator, find all points, like x and y coordinate, of horizontal and vertical tangency to this parametric graph. So just like, this isn't the graph for this set, but the set we had yesterday kind of looked like that. Notice how probably at this point we'd have a vertical tangency, okay, a vertical tangent line. Maybe some other point down the road would have a horizontal, but we're trying to figure out if we were to draw in tangent lines, where could we draw them going up and down and left and right. So that's normally based off the derivative, okay, slope of a tangent line. So maybe we'll first tackle the derivative of that parametric set. So we need the y derivative over the x derivative. Okay, so remember this derivative is representing the slope of a tangent line. What do you want the slope of the tangent line to be if you need the tangent line to be horizontal? What's the slope of a horizontal line? 0, okay? And since this derivative is a fraction, when a fraction equals 0, what part of the fraction should equal 0? Meaning top or bottom? Top, okay? So to figure out a horizontal tangency, we're simply going to set the top equal to 0. What's the slope of a vertical line? It's undefined, right? There's no slope whatsoever. It's an undefined slope. So what part of a fraction should we set to 0 to label it as undefined? The bottom, right? So to figure out a vertical tangent, we'll set the bottom equal to 0. So in each case, we can figure out the particular time during this parametric curve where we have a flat slope or a vertical slope. So for the horizontal, the time would be 3/2, and for the vertical, it looks like we have -1/2. Okay, so that's all well and good. We can figure out the time where we have a horizontal or vertical tangent line, but they wanted the point, okay, the actual spot on the parametric curve. So how do you think we could figure that out? How can we use the times we just found to find a point? Plug them in. All right, so let's see. In the x equation, we would need 3/2 squared, which would be 9/4, plus 3/2. Common denominator would be 4, so 9/4 plus 12/4. Oh, sorry, 9/4 plus 6/4 would be 15/4. And then we got to do the same thing for the y equation. So 3/2 squared, we have 9/4 minus 3 times 3/2 would be 9/2 plus 5. Common denominator would be 4 again. So 9/4 minus 18/4 plus 20/4 be 11/4. All right, so the actual point of the horizontal tangent line would be 15/4, 11/4. We're going to repeat the process for the vertical one. So let's see. In the x equation, if we plug in -1/2, we'll get 1/4 minus 1/2, which is -1/4. And then for the y equation, -1/2 squared, we got 1/4 minus 3/2 plus 5. So 1/4 minus 6/4 plus 20/4. Actually, this would change to a plus because it's -3 times -1/2. So 1/4 plus 6/4 plus 20/4. Looks like 27/4. All right, so we'll say that point is -1/4, comma 27/4. You doing okay? All right, so one other thing we can talk about with these parametrics is arc length. And we did arc length at the beginning of the year, like way beginning of the year, but that was arc length for a rectangular function, like if we had x's and y's. I'm curious if we can dig deep and remember what the rectangular arc length formula was. Nobody there? The hall. I know. Can we think about from the beginning of the year how we found arc length of any regular equation? Uh-huh. It's very similar to this one. We'll talk about the parametric one in a second.
X1 is x2 squared plus y1 is x1 squared.
That's slope. I think you might be thinking distance formula. It's 1 plus the derivative of your function squared. We used to know that back in October. We used to know that. Let's try to remember that for May, okay? All right, so rectangular arc length, if you have an f of x equation, that's how we can figure out the length of the curve from a beginning point to an ending point. Parametric, though, we don't have just one equation. We don't just have an f of x, okay? We have two equations, right? So notice how the integral for arc length for parametric equations is very similar to the one for arc length, or for a rectangular arc length. Just instead of 1 plus the derivative squared, we have each individual derivatives being squared. So from the example from yesterday, we would be able to figure out the length of this curve that we traveled from some beginning point to ending point using this integral setup. We'll talk about more about this tomorrow too, kind of how that relates to vectors. But we have another arc length, and notice how it's very similar to the one we did back in October. So we're just going to check out a quick example of this one. It's pretty easy because it will be a calculator question. That was a typo on my end that said without a calculator. It should have said with a calculator. Okay, so we're going to try to find the arc length of that parametric set. So integral from 0 to 1, square root, and then we need the sum of each individual derivative being squared. So the derivative of the x parametric equation would be 2t, and then the derivative of the y parametric equation, we would have 12t squared. So you could just leave it like that and type it in your calculator. Maybe you want to clean it up a little bit. This would be the square root of 4t squared plus 144t to the fourth. You can type it in like that too. What'd you get?
I don't know if it's close. I got 420 and 490.
Yep. That's good. All right, so there's the length of the curve. Are we doing okay with parametric derivatives? Okay, the second derivative, I know it's kind of crazy. That's a very rare type of question, but the big thing is the first derivative, and it's pretty simple in my opinion. We just take the derivative of the y over the derivative of the x, just like dy over dx kind of signifies. Okay, we'll stop there for today. Tomorrow we're going to get into kind of vectors and how those relate to parametric equations. Just as a general consensus, have we worked with vectors before? Some yes, some no. Maybe you have in physics, maybe you haven't. You may have? Okay. We'll check out vectors tomorrow. We might have to do a brief kind of intro to them.